everyone online is hearing me well.
All good.
Perfect. So I'll be talking today about multimodal behavior modeling and the work I've been doing for the past kind of 10 years almost. So I've joined the school almost a year ago, and I don't know where the time actually passed because so I joined last October. And before that, I was at University of Cambridge for about 10 years where I had my PhD and a postdoc for a couple of years and a research fellowship. And today I'll be touching upon many projects that I've been working on and showing some results from all projects and some also kind of insight about what I would like to do or what I'm doing at the moment as well in these projects. So in general, my research background is this work on like affective computing, social signal processing, and human behavior understanding with many applications on different domains. And in general, if I want to describe what I'm doing, so basically it's building on some domain experts. That could be psychology, psychiatry, maybe animal behavior science, and builds data-driven models that can make us actually build tools that can help the domain experts back again to basically, and maybe inform them in some of the research questions that they are working on. I have been actually focusing on computer vision. So computer vision is the main kind of area I'm working on, but generally speaking as well. So as we know, I mean, many of these fields uses sensors. So the sensors can be videos, audio, wearables, etc. So my main research was mostly focusing on vision, but also keeping in mind multimodal systems development. And when I mention multimodal, it's not only multimodal as in the sensing modality, but also multimodal visual cues. So lots of work for human behavior understanding, many work would look at the facial expressions, specifically maybe some of the body movements. But I focused a lot, I researched a lot of work on gestures, specifically affective gestures or affect displays or self-adapters. And I mentioned here, when I talk about gestures, it's really, really quite a huge field. And I mentioned here one of the very kind of famous work of Ekman and Friesen, where they looked at the classification of the body movement. So we know like lots of the Ekman's kind of FACS coding system, which is the system to basically code the facial expressions, map them to emotions, etc. But also they talked about body as part of a classification of the body movement and classification of how these body movements help us actually we express a lot of things through these body movements. And I mentioned here, I'm also, when I mention body expressions, lots of times we get the word, people ask about the culture. And yes, there are actually some of the body movements that are mostly related to culture, which is like the emblems, which these are kind of the victory, okay signs, etc. Illustrators, these are some other types of gestures that are related to speech. Lots of people work on that. I haven't worked on that side of gestures, but these are basically gestures that are accompany speech. So I can say I went that far or that big. So these are, again, related to the speech or the actual content, the verbal content that we talk about. Regulators, these are actually what we do to regulate in conversations. So it could be kind of turn taking, etc. The two that I'm actually interested in, and probably I'll talk about a lot in this talk, are adapters and affect displays. So these are actually, they are a subset of these body expressions that actually, according to Ekman and Friesen, we do express emotions, mental states, some of the self-adapt to the environment using these kind of gestures. So that's in general kind of a background of research areas I've been interested in. And one of the first projects that I worked on working under this umbrella is looking at hand-over-face occlusion. So this is kind of a body expression. Let me actually mention as well something about what I'm doing here. So I'm interested in this novel mid-level gestures. So for example, many of the related work, many of the data sets now will have the facts coding, like the action units coded. And we know that these are kind of, we can just extract those. These are a micro behavior that we just extract them, and they actually tell us a lot about the facial expression. When we talk about the body, less kind of taxonomization or less coding is done for that. Lots of work just looks at general body movement, but actually very, very, very few. I mean, nobody actually talks much about how we can actually look at these specific gestures and give them a coding and maybe use them later on as similar to the facial PACS coding system, for example. So the first, like when I started working on that, I was thinking, okay, facial expressions, we have the facts. What happens when the hand actually touches the face? We basically think, oh, that's noise we need to get rid of because it messes up with the facial expression analysis. So I did some work on like detection and classification of these hand over face gestures. And this included basically doing the whole pipeline, starting from the data acquisition to taxonomizing and coding of the gestures. And that was based on basically the data that we collected. So we basically brought people to the lab, and they actually were solving puzzles together and talking together. And we actually recorded these interactions. And then we extracted kind of based on event-based, kind of the time when there is any kind of expression happening. That includes body expression, face touch or non-face touch as well. And then we coded all the hand gestures in this interaction. And again, lots of work has been kind of, okay, thinking how we can code the gestures. So we decided to do it based on hand shape, hand action, and the facial region occluded. That all has been coded. And then there were two parts. First part is, can we actually automatically detect these kind of gestures using machine learning? So can we have a system that can detect, we can say, okay, there is a face touch on the cheeks, a moving hand on the forehead. This was kind of the big aim. So coding the gestures and automatically detect them. And we built a system that basically managed to do that to a certain extent. But also the second question was to see, does it actually help at all? Or is there any correlation between these kind of gestures and the emotional content or the mental state? Because I mean, the word emotion is a little bit tricky. I like to use the word mental state because that includes as well thinking. I mean, it's kind of everything that we do. It's not only the emotions. I mean, it could be confused, unsure, etc. And for that, I used actually a taxonomy that was developed by Simon Baron-Cohen in the Department of Psychology in Cambridge, where actually he had this kind of taxonomy of different kinds of mental states as they see. It's just kind of an exhaustive list of all kinds of mental states and categorized in a certain way as well. Just kind of a taxonomy of how we express these kind of names. And we did actually, here we see, we did find, first of all, this was kind of one of the first studies that looks at that. The data set was at the end of the day a bit small because we did all of this collection, all the coding basically in the department, like just was kind of, yeah, in-house. So at the end of the day, when we looked at the amount of face touch, it was about 20% of the time. And this meant the data was even smaller. And we looked at how does this correlate with different mental states. We did also some labeling. So we did, the labels were not actually our own labels. We just put these segments of video online and we just asked people to label, what do they think these people are doing? Again, there was lots of videos as well that we actually excluded because maybe there was no enough agreement, but we just got the subset where there were enough agreement, inter-rater agreement to make us sure that actually we can conclude that this mean, this gesture or this expression mean this kind of emotional label. And we found correlations between some of the like this kind of gestures on the face and cognitive mental states. So like when the people are thinking or confused, there are these kind of gestures. And while we want to look back actually in psychology or any of the work that has been done before, that does it talk about does these gestures really has this kind of relationship? And actually it was true. There was some very old work that people were talking. I mean, many of the previous work was very not experimental, sorry, kind of qualitative. So there was actually kind of, there is work from psychology that says that usually we do this kind of self-touch or just this kind of face touch when we're formulating an idea, but then we express, when we start talking, I do actually kind of do this out of body gestures to express the idea. So this was one of the first projects I worked on. And recently as well, we're planning actually to take that actually a bit. So this is the first study that looked at hand-to-face gestures, and we're planning to move this a little bit forward actually with actually Rachel Jack here at the School of Psychology, to basically try to have again a more taxonomy, a more formal framework, because I still believe that's really important, but not many people have been working on that at all. So we're planning to try to use also kind of data kind of synthetic videos as well, synthetic images, and try to actually have some kind of a big taxonomy or a code book for these kind of gestures. My work on like vision-based AI for mental health support. So I've been working on this. I mean, the mental health kind of condition I'm interested in is what we call psychological distress. And psychological distress is just one of the I mean by psychological distress is like depression, anxiety, and general stress. That's actually kind of the most common kind of when people are, I mean, the number of people suffering from psychological distress is very high. And according to statistics, not everyone actually see a professional on time. And so I'm interested actually as well, can we have some automatic detection tools as well that can find these behavioral biomarkers. These can help as objective tools. They can as well, I mean, if I'm actually feeling unwell for a little bit, the amount of time I will need to actually reach a psychiatrist who's actually the actual person, the actual expert, is really very long, especially in this country. It's not easy. If we can actually build models that can actually encode the kind of the expert knowledge, which is the psychiatrist knowledge, and actually bring it to kind of the first line of support, that could be a GP, a peer support person, or a lay health worker, that would be really a very good kind of a step. Because then the model will encode this expert knowledge and actually bring it forward a little bit. So the general kind of the usual assessment for this kind of for depression, anxiety is this kind of self-assessment, which is just questionnaires that people would just fill. So if I'm feeling a little bit like unwell, I would go to the GP. Probably they will give me questionnaires to fill just to ask about if I'm depressed or anxious or something. So that's kind of the usual way. But can we actually do this somehow automatically? So I started working on this project really some time ago when I spent the summer at University of South California at ICT, and these videos I worked on a big project that was one of the very first project that looked for audiovisual behavior descriptors for psychological distress analysis. And it was working with a data set that was labeled for depression, anxiety, and PTSD. It was a very big project and many people were involved, including Stacy Marcella, who's I think still affiliated with the University of Glasgow, and he was there at that point. And it was one of the first projects that we're looking at, can we automatically predict some of the behaviors? And if we can automatically, based on using machine learning, or even just simple correlation at the very beginning, correlates with the questionnaire results. So can we just, by looking at the person for a little bit, even if that person is just talking to an avatar or like in a video session, can we predict the score of their depression and anxiety? And at that time, and I guess actually still till now, not much has been, I mean, most of the automatic signal that's extracted is from the face. So all action units, so facial landmarks, some of the head motion, the gaze, and general body movements as well. So here there was kind of general, how much the person was moving around. So these kind of signals were actually specifically chosen because we had sensors that can do them automatically. At that time, we still actually, I think there is lots of very good systems that can extract these kind of facial expressions and behaviors from now. But also because they actually matched a lot of previous literature, that there is actually lots of qualitative work that says specific movements of the body, the amount of eye gaze, the amount of smile does correlate or actually appear maybe more often in like a depressed population compared to non-depressed population, etc. And this is kind of a list of related work in this domain. what I was interested in, and my part in that project, was basically the body expressions as well. Again, the only way to actually measure body movement was just general body movement. So just we're actually collecting how much the people moved around. But actually there was, again, from literature, that there is this kind of behavior that's called fidgeting. It's still part of self-adapter. It's this fidgeting behavior, like when a person is just kind of rocking around, just like touching kind of their body in a certain way, that they are actually rated, they are supposed to be soothing kind of gestures that people actually do more when they are depressed or anxious. And I find myself kind of rocking so much if I am actually anxious. So it does happen. And we all actually probably experience some kind of that with different level. So at that time, we also looked at fidgeting behavior, but we did label it only manually. So the results of the work, it was kind of a very good, it's again, a huge body of work. We did lots of analysis between these kind of automatically detected signals and the scores of the distress, which includes anxiety and depression, and non-distress, which was kind of the people who were not under that, the kind of normal or non-distressed population. And we see here that there was actually significant differences between the groups in terms of different behaviors. So for example, the eye gaze, the smile, and also as well, the amount of self-adapters and the amount of which is this fidgeting behavior. And at that time, we did label it again manually for different locations: hands, like hand on hand, hand on legs, kind of legs fidgeting, etc. This kind of fidgeting behavior. So that work, this was kind of the first work when I started thinking and looking at that long time ago. But then recently as well, I wanted, okay, why we don't have actually a way to automatically detect fidgeting? Again, this is kind of a mid-level feature we don't look at often. And it is actually from experimental work before, from psychology, it is related and correlated with many actually psychological distress. Actually, it's not even important in depression and anxiety. It also appears in autism. It appears in many other kind of psychological disorders. So wanted to work on that. And I want to mention one of the challenges usually if you have an idea you want to work on and it's completely new, is that especially in the domain of the healthcare, many of the data sets are private. So it's very hard. So it was fine to work on the data set when I was there, but once I'm back in Cambridge, I couldn't access the data. Actually, many data sets are available, but only their features. And by the features, I mean, okay, the facial expressions, maybe the audio, maybe the transcript. But if you want to actually predict a new behavior or do something that's completely non-incremental, it's very hard to do this with just the features, because the only thing you can do is just, you're really basing all of your algorithms on other system outputs, like the systems that are already there, like facial expressions, etc. So nothing like if I wanted to look to completely different gesture, it was difficult to find this with what's available. So we decided, okay, let's bring people and actually do the experiments ourselves. Let's build our own data set and see if we can detect this behavior, build kind of a trained model that can detect this fidgeting behavior. So that was the well-being data set. So we basically, again, invited people to the lab. We had this kind of semi-structured interviews, just talking with them about life, really, nothing fancy, nothing clinical. And then at the end of the day, we collected the questionnaires for their scores for depression, anxiety, and general stress. We had about 35 interviewed subjects. We did initial screening first before the people come, because we were interested to balance the data sets. So we wanted to get from all kind of distress kind of scores. So we asked the people to actually fill the questionnaires when they were interested to join at the very beginning, and we chose basically a good sample that can cover all kind of aspects. So people who are high on the depression scale, people who are low on the depression scale. But then at the end, when they came to the lab, because some of these questionnaires are very as well, kind of the questions are actually relates just to the last week or something. So you can't just depend on the initial one. So we asked them to fill another one just to be really confident on the scores that we take on the spot that are next to this interview. And we wanted to detect fidgeting, how much people fidget in general. Can we detect fidgeting behavior in this data set? So we did some kind of, again, first step, the most kind of time-consuming step is coding. So we had 2 coders just to sit and code the fidgeting behavior. It was semi-manual coding because because we made use of just open pose where you can detect the joints location, so we know when there's kind of a occlusion, kind of 2 joints crossing, so we're hand on hand, hand on legs, and then we just pick those segments, and these were the parts that we did all the manual coding, and we taxonomized it as well. So like hand on hand, hand on legs fidgeting. There was kind of a long taxonomy for them, all data driven. And then we built kind of a simple detector that just uses some trajectories, the movements of the different body parts, and for this kind of analysis of short segments that we found this fidgeting behavior in to detect self-adapters. And this is actually a demo of what we... So this is not from our dataset. This is actually from another dataset. So a way to really try to test the dataset and without really sharing the videos is we asked basically actors or people to actually just act exactly like the natural videos that they saw. So they're really people here. I mean, they are not really depressed. I mean, they are just students. They were just copying the gestures that we saw in the video, so that we can, one reason for that, again, you need the work to be reproducible, you need a benchmark so people can test even if there's some future work on the same work. I mean, if I say I tested this on a data set and it's private, so nobody can even compare, but I say, okay, I tested on the data set that has the natural expressions, I show these numbers, but also I tested in this benchmark, that's available, and you can actually improve on that benchmark. So again, it shows, it does this classification of the twiddling and yeah. Okay, so first step was always this kind of a detection of the behavior. Second step, can we add that in the multimodal system to predict? I mean, is it useful at all? I mean, the hypothesis was that it is useful, but is it actually useful? I mean, does it have any content that we can use for prediction of depression and these scores? And then comes, so we tried with different kind of architectures to combine all of this multimodal signal. Again, that's one of the challenges of working with these kind of data sets. I mean, you have a 15 minutes or half an hour of video that includes video information, audio information, lots of fidgeting, lots of movements. It's very noisy signal. And the score at the end is just one score of depression. So the amount of dimensionality of the data you're handling is huge. And you want at the end to just get the most salient discriminative features out of that and get rid of any noise. So that's one of the challenges with working with these kind of data sets. End-to-end kind of deep learning wouldn't work, but what kind of features to extract and how to combine them together. So we tried using auto encoders, again, encoding all the fidgeting behavior, gaze and AU. These are the common facial expression FCCs from the audio, and we encoded, so this is just to get a representation per frame, and then we encoded them per video using Fisher vector and Gaussian models, and yeah, and just tried to simple at the end logistic regression for it. These were the results, was like trying different kind of mix and match different modalities. Sure.
Simone has a question in the chat. I don't know if you want to take it now or at the end.
I don't see. Can you say the chat? I can't find.
I'm happy for it to be done at the end. Just carry on, Mara. I'm okay. Just framed up my thoughts into chat.
Okay, we'll keep it till the end. So yeah, so what we found is that the nice thing about so we managed actually by having all the signals together to get about 82% accuracy. But we see as well that actually the detected fidgeting behavior increased the performance of all kind of the modalities. So this was actually quite interesting, which means it really has some extra information that can be useful in detection of psychological distress. And that's like depression and anxiety. And actually, I combine them together as well because they are usually, there is lots of correlation and comorbidity between them, but that's kind of a different story. So here you can see both of them, but somehow, I mean, the detection of both of them goes and they go together. We tried also with some other architectures as well that uses, again, temporal information. I mean, for the previous one, the temporal information just were combined at the very end, but this one, can we actually just try to see the temporal information in every modality separately? So, and this was kind of, again, an architecture of kind of a late fusion rather than early fusion. And I will not go into a lot of details. This one as well, we added the audio, the transcript, the text information, just very simple kind of paragraph vector, classification. And we added them as one of them. And we had at the very end what we called an adaptive non-linear judge classifier. So it's basically, it takes the information it gets from the three kind of independent classifiers, and then at the very end, do some feature selection, and based on them as well, and based on the trained data. I mean, we train this as part of the data, and based on it decides from where to get the most important information, depends on the video. Again, using temporal actually increased the performance. We reached 87% on our data set. So the one down there is this well-being data set that we actually compared with our previous work. But also we tried it on a benchmark data set that was that's actually available on bipolar disorder, and it's actually improved as well the detection for that one. And that's one of the data sets that are available for one of the challenges that has been around for a while. Back to the idea that actually I think that these models as well useful to feedback something to the experts. Can we actually see what are these? Because always when these kind of multimodal system, maybe many of them are really, we add modalities and then we get better results, but are they actually just redundant information? I mean, many of them are correlated, many of them are, there's loads of, I mean, these signals correlate, many of them could be, is it redundant? Maybe it's already appeared in some other modality. So we tried to do also this ablation studies and try to see, so this graph is actually showing the percentage of the videos where every modality were able to extract, like to get the correct result, the correct kind of score for this amount of videos. And we see here from the mix that actually they are so much interrelated, so they're all important. None of them are completely hidden in the other. So it's like none of them, every one of them separately could find something in some of the videos. So it shows as well how they are kind of important, all of them, and it's not, none of them is kind of redundant information. Okay, so I'm still interested in continuing that work, looking at this novel mid-level features. I mean, there are some features that we kind of take for granted that they are good, the systems are done, facial like the fact scoring, some facial action. Can we actually do something similar for other behaviors as well? And looking at this multimodal, multidimensional systems as well, how can we combine all of this signal and to get something useful for these domains? Okay, last topic, or before the last. So do we actually, these facial expressions, or how we express, is it only for human? Do animals express emotions or mental states? So I'm not the first one who said that. Actually, this work is as old as Darwin. So Charles Darwin book, one of the very first works that looked at expression of emotions in man and animal, actually had some photos of talking about dogs, how they can express, like this one is like hostile intentions, this one affectionate, this monkey may be smiling. So Darwin talked about this expression of emotions in animals really long time ago. Why we want to look at the facial expressions of animals, or why we want to know if the animal is happy or sad? Actually, it can be more than just knowing their emotion. It can be more about early detection of diseases. So I have been working on this project for like 3 or 4 years, mainly working on sheep. And sheep specifically, but same as well for cows and horses, are prey animals. Some of the diseases that they have that can be contagious are painful. And they might be wired actually to hide the pain because really showing signs of vulnerability is bad for predators. So if we can have continuous screening of these animals, this means we can actually pick early signs of diseases early on and actually being able to intervene quickly and saving a lot of time as well of the people who are taking care of them, and maybe saving the time of like these contagious diseases that might be move around in a flock. So I've been working on sheep with, again, collaborators who are animal behavior. Krista McLennan specifically is kind of my main collaborator. We've started that work together. And that's because we're computer scientists, we need a code. I mean, give me a coding or something so that I can actually do this automatically. I can build a machine learning model. So this is based on her work on like this Grimace scale. So she developed the Grimace scale. If you look at it, it looks very much like the facts somehow. So it's like, again, it looks at changes on the face, changes on the cheeks, changes on the mouth and in the ears. And what they used to do, I mean, the aim of this is that they can basically, looking at the face of the animal, mark these different changes in the facial expression and have a pain score at the very end, which can basically tell us about the health of the animal, because these, I mean, we don't inflict pain at all. So the data sets we worked on were actually for either healthy animals or ones who had painful diseases such as mastitis or foot rot. So how can we do that? I mean, one can think, oh, I mean, we can do this for human facial expression. It must be easy for animal facial expressions as well. But actually the work on human facial expressions have developed over the years. Thanks to the big data sets, millions of images, annotated images and millions of incremental systems that has been going for a long time to improve the accuracy. If we want to do the same for animals, we really need to go through the whole pipeline from the face detection to the landmark detection, defining of the landmarks, defining of what we're interested in, and then generating the pain level or the disease level, as I will show. I will not go into loads of details of implementation, but there's lots of transfer learning that's done in this, because there is lots of work on human, but actually we can't use the same models. It's impossible. For example, in human facial expressions, we never code the ears. I mean, we really don't use our ears as good as our fellow animals. So we really need, while ears is really, really very important for animals. So we can't use the models as it is, but we can make use of all of this kind of develop models that for human facial expressions. So again, we did work on face detection. We used, again, some single shot stuff. We defined landmarks. We started by just 7 landmarks. Okay, what are the important landmarks in the animal, in the sheep face? Good question. I mean, at the beginning, we started by maybe 7 landmarks on eyes, ears, but then at the end, we wanted, okay, can we do something that's really as good as the human facial expression that can detect all the kind of points? Again, another challenge with the landmarks is that in animals, the amount of self-occlusion is huge. So again, my profile face is not as bad as like the sheep profile face, because like you really can't see, half of the landmarks are completely hidden. So for the facial landmark, we did something a bit, actually my student Charlie is the one who had this idea, is really to make use of fine-tune a human head pose estimation. So we detect the pose first and then detect the landmarks, because the number of landmarks change depends on the pose. Okay, and the last step was like, at the very beginning, can we detect the pain level? And for that, when we started working with this, we decided, okay, we do something very similar to human facial expression. Let's define a FACS action coding system. So we define this kind of difference. So action unit 1 is like the ear when the ear is not flipped, and then when it's a bit rotated, when it's completely flipped, the nose shape, etc. And then based on that, can we predict the pain score? And this was kind of a very early model of the system that actually we did a demo for it on BBC Country File. And I'm very proud of this photo because I took this photo of Adam Hansen's sheep. And at the very first, the first model of our system as like similar to any of the facial expression detection models, it doesn't work that well on the profile faces. It really wanted, we wanted kind of a frontal face so that we can show just good results. So I asked Adam Hansen to basically, how can I get the sheep to look at me? And that's the question that you will tell me, how I made the sheep pose to the photo. And we managed, so the idea of the system was really to look at these, as you see here, different regions of interest, changes on the sheep, on the face. For example, it's picking the left ear is flips and the V-shaped nose, and then predict if, basically give a probability this animal could or could not be, like the amount of pain. We actually recently did some work as well to remove the human from the loop completely. So at the very beginning, when we started working on this with the animal behavior scientist, the main aim was really to have the model to mimic what they have done. So what they have done is really to look at kind of labeling these kind of different landmarks and decide that this looks like, the eyes looks like that it has pain, the nose looks like it doesn't, etc. But we tried to do kind of an end-to-end classification to just predict the disease directly without detecting the pain. So for the last data set we worked on, we had these animals that had, we knew that they had diagnosed with mastitis or foot rot. And then we have their videos of them after 40 days of treatment. So we know that at the very beginning they are sick, at the very end they're not. And we changed the classification task is really not to detect pain, but detect the disease. So, and that's the main aim. So can we predict the disease as early as possible in the pipeline? So that's still kind of work in progress. Again, because I'm interested in multimodal, can we look at also body expression of sheep and some multimodal analysis? And that's kind of the next step, looking at, again, body parts, automatic detection of body parts, and detecting gaits analysis, etc. Okay, so that's all about animals. I will not talk about this project. I just wanted to mention briefly that I've done some work on enhancing drivers' experience using vision research. If someone is interested in talking about that, this was a project funded by Jaguar Land Rover, where we looked at, again, the behavior of the driver compared with the car information as well. And we looked at, like, the two projects I was particularly working on was the monitoring the driver distraction and drowsiness detection. I'll not go into a lot of details, just wanted to mention them. And I can actually talk about them offline after that. So thank you very much. These are acknowledgement to my students and kind of collaborators who actually I mentioned many of their work in this presentation. So thank you very much. I'm happy to have questions.